if you remember, before dimensional analysis, we were talking about the head losses. In other words, the frictional losses inside the pipe system. And if you remember our famous equation, which was saying that P by rho and the V squared by 2G and the plus Z, and this one was for the inlet, and the plus, if there is pump, you can add the pump, but if in any case, if there is no pump, I will not add anything, and this value will be equal to, and the P by rho plus V squared by 2G and the plus Z, and this one is for the outlet. And we have said that these two quantities are only equal when it is ideal. Okay. This is for the ideal case. But when the reality comes into the picture, you will not have these equations, but you will have the plus the losses part. Okay, and this is the losses. Now today we are going to quantify the HL, head losses. Okay? And how do we find it? How to determine HL? Because in the previous questions, HL was given, or the question was given such that the HL can be determined. Okay, but in these slides, you will see how do we calculate HL. Okay, what is its formula at the end? Okay, this will be today's lecture. So firstly, I will introduce you the laminar and the turbulent flow. Okay, there are two famous types of the flow regimes. Okay, you can see that flow regime. One is the laminar, and the other one is the turbulent. So what is the laminar flow? And let me give you one example for the laminar flow. Say that this is the pipeline. Okay, this is the pipeline, and inside that pipeline you have fluid flow. Okay, you have flow. So to understand the behavior of the fluid flow, I need to see the particles of the flow. But since the flow is transparent, I cannot see it. But the only method that I can see is that I can inject dye into that fluid, dye or ink. What you are doing is that you are injecting ink into that fluid. And when the ink flows in that straight line, you can see it is a straight line. Okay, it is not diverged to any. Okay, so it is only a straight line here. I will try to make it as straight line as possible. So this one is called the laminar flow. The fluid particles, you can see that fluid particle here. The fluid particles follow straight line. Okay, and if I, for example, inject the dye at this location, and the fluid particles again will flow in horizontal line. If I inject the dye at this location, the fluid particles will flow in that horizontal line. You can see there is no crosswise component. No crosswise velocity. So that is the laminar flow. In other words, if there is no crosswise component, it means that no mixing. Okay. In laminar flow, you cannot have the mixing. You can have the mixing, but only due to that no mixing. So the mixing only due to diffusion, let me say. Mixing only due to diffusion. And this is the laminar flow. But in another extreme of the flow regime, there is also the turbulent flow. Okay, and for the turbulent flow, if I will inject the dye again, so that this is the dye or ink. You are injecting the dye or ink again, and in that case, the flow will be. Let me show the flow to you. So this flow regime for laminar flow, it doesn't change with respect to time. For example, if I inject the dye at time t0, okay, or time t1, or time t2, in all of the times you will see a straight line. It does not change. But for the turbulent flow, I will inject the dye at time t0, and the fluid particle will go in that way. Okay, this one is for time t0. Now I that inject the dye at the next time, different time. Let me draw it as with a horizontal with a different color so you can see it. So now I am injecting it at a different time, the time t1. These are all fluid particles, okay? I'm injecting the dye at a different time. Okay, this is time t2. and I'm injecting the dye at a different time. You can see time t3. You see that fluid particles from the same location, they don't follow the same particle trajectory. Okay, they are flowing at different trajectories, at a random trajectory and unpredictable trajectory. And this is called the turbulent flow. And the characteristics of the turbulent flow is that it is random, okay, and it has that good mixing, very well mixing. Okay. You can see the difference. The mixing in the laminar flow is only to the diffusion. Okay, this is molecular level. Okay, and for the turbulent flow diffusion, very well mixing. It means that the mixing process happens diffusion as well as at system scale. At system scale, or you can say that macroscopic regime. Macroscopic regime. And this is the turbulent flow, next behavior of the turbulent flow. So to understand why diffusion is a slow process, I can give you one example, say that, for example, perfume. Okay, if the perfume, this one, so that smell of it spreads to the room only by diffusion, okay, smell of perfume, only by diffusion, okay, only by diffusion, and you will need days, okay, to feel it, to smell it actually. But the smell of perfume inside the room, it is not only by diffusion, it is due to the motion of the air currents that we cannot see it. Okay. But if it happened only by diffusion, only by laminar regime, you can say, you will need the days to smell it. But for the turbulence, it is not a problem, because turbulent, you know, it has the diffusion, it has the system scale mixing. That is another important thing about the turbulence. And it is also, that is the turbulent, it has high inertia. High inertia. It has very high inertia, very high kinetic energy, you can say, so that you cannot predict what will happen in the next time. So it is, and also the first one, which should I add, very complex. Okay. And since it is very complex, and it is, you know, that only experimental, mostly, let's say, not only, but mostly experimental. Okay. This is another bad side, the drawback of the turbulent flow. Okay. And the 5, and due to that, due to 4, let me say, due to 4. Very complex, okay. And there is no theory on turbulence. No theory on turbulence. Because it is a very, you know, that problematic side of the fluid mechanics. There is no theory on turbulence, and the turbulent flow regime solutions for this one is a 1 million prize. And if anyone solves the question, the flow behavior in turbulent regime, you'll get $1 million prize. It is a mathematics Clay University Institute prize. Okay, now how do we know that the flow is turbulent or the flow is laminar? We determine it by the Reynolds number. Okay, the Reynolds number. And the Reynolds number is that the density of the flow multiplied with its velocity, multiplied with its diameter, and divided by the viscosity. Okay, this is the Reynolds number. And if you look at the units of this one, it is dimensionless. There is no any unit for this one, dimensionless quantity. And if it is a laminar regime, if it is for the first one, the Reynolds number should be less than 2300. It should be less than 2300. But if it is turbulent regime, the Reynolds number should be greater than 2300, and this is called the turbulent flow. But in reality, it is not the 2300s, but it is 4400s. But these are, you know, that these are approximate values, because 4400s, and between 2300s and 4400s, you have the transition regime. Okay, Transition regime means that it is neither turbulent nor laminar. It is in between. Okay, sometimes turbulent and sometimes laminar. It is transition. Okay? It doesn't show an exact behavior that you can say it is laminar or the turbulent. Okay, this is the Reynolds number. Okay, good. But the issues that we have talked about only was for the internal flow. Okay, now what happens if the flow is external over the body surface? Okay, you can see it is external over the body surface. Now we will see it. Okay, just 1 minute. Okay, so if the flow is external flow, and then what happens to flow when it is external, when it is over the body? For example, airplane, or that it is over the cylinder. Okay, the flow happens over the cylinder. Okay, and what is the flow regime when it happens over the cylinder? Now let's see it. Just 1 minute. Okay, so you have just 1 minute. Okay, so this is the external flow over airplane, and this is the external flow again, flow over the cylinder. And these of these two flows, flow over airplane, flow over cylinder, so that Reynolds number about 10 to the power of 5. Okay, it means that it is that more than 10 to the power of 5, it is turbulent. Okay. That is therefore external flow. But for the internal flow, we are talking about the 2300s or 4400s. Okay. Now there is a question, and you can actually find the Reynolds number for the airplane. So the Reynolds number for airplane, so that will be equal to rho velocity. And for the airplanes, we don't take the diameter of the airplane because there is no diameter concept in airplane, but we are taking the chord length, average chord length, which is a distance. So if you think this one as an airplane wing, so this is the airplane wing. We are taking the distance as this one. Let's see, chord length. Okay. And for that chord length, average 4 meters or 3 meters, you can calculate chord length. Okay. And you can calculate the Reynolds number for the airplane, and the velocity of airplane is that, say that 300 meters per second, and that's a 200 meters per second, and chord length is 3 meters, and the density of air is 1.2, and the viscosity of air is 10 to the negative 5. Okay. And from these quantities, you can calculate the Reynolds number for the airplane. And if you have value, you can tell me, and I can write the value here. Okay, if you have the value, you can tell me. Okay, let's see what is your value here. Okay, but you can also similarly calculate so that flow over the cylinder. This one is the cylinder, and for the cylinder, you take the diameter. Okay, the diameter of the cylinder, again, you can calculate for this one. Reynolds number will be rho v, and the diameter of the cylinder divided by mu. And you can notice that this length here, it is not the fixed length that should be always diameter. And sometimes it can be chord length, sometimes it can be diameter, sometimes it can be length. Okay, it depends on the application of the equation. Okay, that is 72 times 10 to the power of 6 times 10 to the power of 6. Okay, that is the Reynolds number for the airplane. And therefore, this regime is the turbulent regime. But what they are doing is that the airplane wings are very smooth. Okay, and you know that turbulent is all about the disturbance. Okay, if you keep the flow that is ordered manner, you can get the laminar. Okay, but if you disturb it, you can get the turbulent earlier. But what they are doing is that they are having different configurations on the wings to keep the regime as the laminar. Okay, to keep the regime as laminar. So I can give you what turbulent feels like. That is very. So that there is a famous proverb that says that turbulent is like, that is the turbulent. You cannot know turbulence, but you can feel it. You can feel the turbulence, and you can feel the turbulence. So you can feel it in airplane. So you can feel the turbulence in airplane. So when the airplane is in turbulence, you can feel the instability problem with the airplane. It becomes unstable, but if it lasts longer, then the airplane can, you know, that it can destroy the airplane. It can be unstable and dive into the ground. But they are always trying to keep the flow laminar over the airplane to keep it stable. Okay, you can feel it. This is a famous proverb. You cannot know it, but you can feel the turbulence. Okay, there is another question, but this one is for internal flow. Calculate the Reynolds number of blood flow through aorta of diameter of 2 centimeters. Okay, and the velocity of 38 centimeters per second. And the viscosity of blood is 4 centipoise. So that the viscosity is 4 centipoise. And the specific gravity of the blood is 1.05. And what happens if the flow was turbulent? The question itself says that it should be laminar, but what happens if the flow is turbulent? Now let's see it. The Reynolds number will be for the blood flow rho Vd by viscosity. And the density of the flow is 1.05 is specific gravity. And therefore density will be 1050 kilograms per meter squared. Okay, and multiplied with the velocity, which is 38 centimeters per second, it will be 10 to the negative 2. Multiplied with, that is diameter, which is 2 centimeters, it will be 2 times 10 to the negative 2. And divided by the viscosity of the blood, 4 centipoise. 1 centipoise is 10 to the negative 3 kilograms per meters second. And the 4 centipoise will be 4 times 10 to the negative 3. Okay. And if you have the value, you can tell me what is the Reynolds number of the blood. Aorta, aorta, this one is the largest vein. Okay, it is the largest one. So that it means that you can that experience the largest Reynolds number here from this aorta. Okay, so 1995. You can see it is laminar. The blood flow is always laminar. But the question is, I can ask your ideas. So what do you think? Why the laminar flow is better for the blood rather than the turbulent flow? If you have any ideas, you can write as a comment. Why the laminar flow is better for the blood instead of the turbulent? What do you think about it? You can actually see it from this picture. Okay. If you have any ideas, let me see your ideas. Why the turbulence is not good for blood flow? The laminar is better. Okay. For don't hurt the boundaries. Yes, Reza. All right, my friend. So the problem with the turbulent flow, you can see for laminar flow, no crosswise velocity. But for the turbulent flow, you will have the crosswise velocity. So it will create additional pressure on the blood. So the additional pressure on the boundary. So this is the blood boundary, and this is the flow. If it was laminar, it is laminar actually. It flows like that. But if it is turbulent, you can see, so it can hit the blood boundary. So this one can create additional stress. So it can create additional stress, and plus, even it can create noise. This one is very important because when the blood is, that abnormal, so that they feel it, they know it from the noise. If there is noise from your blood, that means that there is something that is not working. It is not normal. Okay, good. Now let's go back to the energy consideration of the blood vessels and the flow regime, or why do we need heart? This is the essence of our today's lecture. So these are the introductions. I will start with this one, which is the plaque in the blood. So you can see this one is normal blood. You can see there is no any obstruction. So this one is the obstacle. And that obstacle is called the plaque. So what happens? So first we will start with the Bernoulli's principle, and then we will talk about why do we need heart, and then we will talk about the flow rate, which is the delta P. This is the Poisson equation, which is very important equation. Okay, now when you have this, that you can say this one is the normal area, which is A1, but when there is plug, you can have this amount of area. Okay, this is A2. Okay. And A2 is less than A1. It is less than A1. Okay. And so if the area is small, and then you can get by Bernoulli's principle. And the Bernoulli says that if the area is small, you will have that velocity 2 is much greater, velocity 2 is greater than velocity 1. Okay. So it means that, so if you think your blood as something like this one, it changes diameter due to plug and gets back. It gets back its initial form. And here you have the plug. Okay. So here this is the point 1 and this is the point 2. This is the area 2 and this is the area 1. Okay. So velocity 2 is greater than velocity 1. And the next question comes that kinetic energy increases due to that one. Kinetic energy 2 is greater than kinetic energy 1. So the question is, where do we get that kinetic energy? So where do you get that kinetic energy? So where does that kinetic energy come from? So you have the increase in kinetic energy, but where does it come from? Where does it come from? So does anybody know the source of this kinetic energy increase? So there is energy increase, but there should be some source of it. So where does it come from? Pressure. Yes, Mohammed, it comes from pressure. Okay. So that pressure drops. Okay, so here you have the lower pressure. And since you have the lower pressure here, and here you have the P high. So here P high, and here lower pressure. Okay, this one. But the blood is in equilibrium. Okay, and equilibrium means that P environment, P surroundings is same as P1. But at P2 the pressure drops. P2 is lower than P surroundings. Okay. And then if the P2 is lower than P surroundings, then it will know that the surroundings will press on it and will close this part. This obstruction here, so next time it will be something like this one. And then it will be something like this one, and the closer, and it comes the heart attack. Okay, so this is the Bernoulli's principle that we are using for this energy consideration, actually, to understand the flow in blood. This is the first thing that we should get it. And the second thing is that for fluids so that can be accelerated easily. Okay, this is very important stuff. Okay, you can accelerate the fluid very easily. But the problem is, what do you think the problem is? Problem is, what do you think the problem will be? To decelerate. Okay, you can accelerate the flow easily, but the problem is to decelerate it. Okay? You cannot get the initial velocity back again. That is the funny stuff about the fluids. Okay, for example, if I have an area something like this one, then if the area drops, okay, and then velocity 2 and the velocity 1, velocity 2 will be greater than velocity 1. But what I want is that velocity 1 back, and then I increase the area to decelerate it. Okay, decelerate it, but you will not get V1 back again. We will not get V1 back again. That is the problem of the fluid flow. And where does that V1 go? That goes to losses. When you decelerate, you will have losses. And deceleration is not efficient. Acceleration is, this one is efficient. Okay, but deceleration is not efficient. This is another important stuff. We will use these ones in our next slides. And the third important stuff is that flow rate, V dot. You can see this one. V dot is that delta P multiplied with pi and the diameter to the power 4. Okay, and then Okay, so the third important stuff is that you will have the delta P pi d to the power of 4 and the 128 mu by mu L. And this is for the laminar flow. For laminar flow, you can calculate the flow rate. Okay, so for example, for this blood flow, you can calculate what is the flow rate. Okay, and if you know the diameter of the blood, delta P of the blood, and even if you don't know the delta P, you can calculate the flow rate. It is constant, doesn't change by conservation of mass, and you know the eta, you know the L, and you can find the delta P that happens in blood flow. Okay, delta P is loss. Okay, and that is the reason why do we need the heart. Okay, that's the reason, because you have the pressure drop. And similar question that comes, why do we need the pump? Okay. You need the pumps because you have the pressure drop. And now we are going back to using these results from our blood flow. Okay, now we will analyze the internal flow that happens inside the pipe system. This is a pipe system, a pipeline. Okay, and we are going to consider why do we have this delta P, loss. You can see the equation. This equation actually is called the Parseval's equation. This is Parseval's equation, and it is a very famous equation for the laminar flow. And we will consider why do we have the losses. So you have the flow into the pipeline system, or you can think this one as a heart, blood flow, or whatever you want. And then when the fluid flows inside that pipeline system, at the boundary here, you have zero velocity. Okay. Zero velocity is due to no slip condition. Okay, and no slip condition, I think that I've talked about this one in the previous slides. No slip boundary condition means that fluid takes velocity of solid boundary. In our case, the solid boundary, the pipeline doesn't move. Therefore, fluid will have zero velocity here. Okay, and this is the fluid velocity that enters to the pipeline system. Okay. It has the same velocity everywhere, which is V infinity, let's say. It has the V infinity everywhere. You can say it is the same. And it enters to the pipeline system. Okay, and when it enters the pipeline system, here at the boundary, you can see at any point on the solid wall, at any point. Even you can go back to the example here. For example, the blood. Inside the blood, you have zero velocity, pipe wall. At any point on the pipe wall of the blood vein, that is the vein, the blood doesn't flow. It is zero. Here, the velocity is zero. On the plug, velocity is zero here. Velocity is zero. Okay, that is the essence of the no slip condition. And then what happens is that this no slip condition of the flow affects the layers of the fluid flow. Okay, it affects, why it affects, you can think this one as that rubbing your palm. Okay. When you rub your palm with each other, the momentum of one palm affects the momentum of the other. And here you have the zero MV, zero momentum. This zero momentum affects the next layer, decreases its velocity, and affects next layer, decreases its velocity, but till some location, okay, until this location. So here you have this amount of, so that this is propagation of friction. Know that friction doesn't have an infinite velocity. So if you have, for example, a zero velocity here, zero velocity, it doesn't propagate into the domain in an infinite velocity. It has finite velocity because this fluid layer and there's another fluid layer here. These are rubbing against each other, and this fluid layer rubs against each other, and this fluid layer rubs against each other. But this one slows down that one. This one slows down that one, and this one slows down that one, and next by next, and next by next. But there is some point that the fluid keeps its velocity. It doesn't decrease its velocity. So fluid keeps its velocity. At this point, fluid keeps its velocity. It doesn't decrease. Okay, and then when you move on to the next location here, so that friction now propagates into that distance. Okay, this is that this part, friction has propagated. Okay, and when you reach a distance L from the entrance of the pipeline system, this is the entrance L. that the friction propagates into overall domain. So this 0 MV here, 0 MV, it affects all of the layers, all of the fluid domain. You can see it, it affects all of the fluid domain here. And this is called that entrance length. This is called entrance length. And from this point on, that this friction cannot affect anymore in a different manner. Okay, this is the maximum that the friction can do. It affected all of the layers, and that's all. It cannot do anything more. Okay. Now what will happen is that this velocity profile, if I connect the lines here, this is the beginning point, and you will have the profile here, something like this one. Similarly here, you will have that friction. Okay, that for these are parabolic. Okay, this profiles from this entrance length doesn't change. Profile doesn't change. And then frictional losses become constant. You have the frictional losses, but they are becoming constant. Till that location, the frictional losses were increasing, but from this point on, the frictional losses are becoming constant, and they cannot affect anymore the fluid layers. And this point on, where you have the entrance length, and this point on, we call it as the fully developed flow. This fully developed flow is a region where you have the constant velocity profile and friction losses that have become constant. Okay, now the question comes, this is the reason of the frictional losses. We can see now that the fluid has entered with that velocity, but here you have the less velocity. Kinetic energy has decreased. That is the reason of the pressure drop. Okay, kinetic energy decreased. And it is due to that friction. But in fluid mechanics, we don't call it as friction, we call it as the viscosity. Okay, and the region that is, for example, for this point on, you can see the lines here. These are the, and this one here, there is also one line here. The part that is inside that line, so you can see these are inside, okay? And these are called, that is, you can say, ideal flow, because this part doesn't feel friction. And the regions that is outside of that one, that ideal flow, is the regions that is outside of it, for example, this part and the rest of it. Okay. And these are all called the boundary layers. You can see that there are two regions. One is the boundary layer, or that we can also call it as the viscous region. Okay. That is viscous region, and from inlet to that point, viscous region increases. But inside that region, you have also that ideal flow that doesn't feel the friction. It doesn't know the velocity is 0 at the boundary. It doesn't feel effect of it. Okay. Therefore, this part is called ideal flow, and this part is called that is boundary layer or viscous region. And the length over diameter, if it is laminar, for this length over diameter, it is 0.05 Reynolds number. But if it is turbulent, you will have the length by diameter is 10. Okay. You should remember that most of the equations, 95%, 99% of the equations are for the fully developed flow, where you have the constant properties, where you have the constant values of the friction and the pressure forces, and that is the fully developed flow that is interested, that is, the equations are valid. Okay, you have also this similar behavior. For example, this one is the wind turbine, okay, and this is the wind. And you can see the zero velocity here, 0 MV. Okay, this is no slip. And when wind blows, this 0 MV affects next layer. It affects next layer because they are rubbing against each other. It's like your palm. I've said it. It's rubbing your palm. It affects next layer because they are rubbing against each other. Next layer, you can see that if the wind velocity, if the velocity is, for example, that is 20 meters per second, okay, you can see that 20 meters per second velocity at a height of, for example, that is 40 meters. After 40 meters, you can see the actual velocity of the wind. But before that 40 meters, you don't see the velocity, the real velocity of the wind. But what you are seeing is that that change in wind velocity. Okay, this is the change in wind velocity, and the profile will be again parabolic. Most of the time, it's parabolic. Okay. This is the parabolic, and therefore, when you install the wind turbine, it should be very, you have to be sure that the wind blades are above the boundary layer. This part where you don't feel the effect of it, where you feel the effect of it, it is the boundary layer. It's again the boundary layer here, and this part on it is the invisible, or that ideal region. Okay, but now you can see the problem with this wind turbine. The lower parts of the blades, this one, so the C is low velocity. But upper parts of the blades, this one sees higher velocity. Okay, so whatever power you gain at the upper parts of the wind turbine, you are losing due to boundary layer at the lower parts. But the better option is that you can put that you need taller wind turbine. A taller wind turbine such that the blades are here. So you have one blade here. You have another blade here. So it should be opposite. And you have the two blades here. So your blades should be above this line. Okay, your blades should be here. It should be above this line here where you don't feel the effect of the boundary layer. So if you have questions, you can ask. Is there any question? No question. Good. So now I will go back to the equations of the fluid mechanics. So these equations are not so important. Okay, what I'm trying to show you is that the real picture of fluid mechanics. You have for real picture the Cauchy equation. Okay, it is valid for any fluid. Don't pay attention to these formulas here. And then you have the Navier-Stokes equation, which is simplified form of that one. It is only for Newtonian fluids, and the Newtonian fluid is that similar to Hooke's law. Okay, it is similar to. So where you have the shear stress is equal to that viscosity multiplied with change of velocity. It is linearly proportional. That Navier-Stokes equation is also simplified. You can see the simplifications for the ideal flow. We call that Bernoulli's equation. You can see, or the Euler equation. The Bernoulli's equation is a special form of the Euler equation. Or you have the creeping flow. It is life of bacteria. Okay, and you have the irrotational flow. Okay, this is again the specific applications of the fluid mechanics. It is used in aerodynamics, mostly for that. And then boundary layer flow, this is where we are interested in. You can see that boundary layers. You can see it is a different chapter of the fluid mechanics. Okay? Boundary layer. This is where you have the problems. Okay, that is the source of problems. If you need pump, there is a boundary layer. For example, if you need a heart, there is a boundary layer. Okay? If you need the heater, for example, for a system, there is a boundary layer. All of the reasons of the losses are the boundary layer. It can be velocity boundary layer. It can be a thermal boundary layer. It can be that diffusion, due to mass diffusion boundary layer. Okay? But all of the reasons are the boundary layer. But if you don't consider the boundary layer, and you will have the Euler's equation. And Euler's equation says that you can always slip, no friction. If you have the boundary layer, you can say that no slip, and you can rest on this that is slide here. You can rest on the slide. And that is the picture where Navier-Stokes comes into picture. This equation not solved. Okay. And you can use Euler's equation of motion, and its special form is Bernoulli's equation. And you can use the Euler's equation where the viscosity is not important. You can see here, viscosity is not so important, viscous effects, and ideal flow. Okay. But you see that on airfoil, you cannot use the Euler's equation here. You can see, you can't use it here. This part, you cannot use it. Why? Because it is boundary layer. Okay. Boundary layer is the source of the problems. But you can use it here because it is away from the boundary layer. It's away from it. Similar to wind turbine here. Product here, you can see, or the pipe flow here. So this part is the ideal flow. It means that you can use Bernoulli's equation. You can use Bernoulli's equation. Here you cannot use it. These parts are the viscous friction. There are frictions. Okay, you cannot use the Bernoulli's equation. Okay, so now we are coming back to our problem. Where do we have the losses? And in pipeline systems, I will not talk about the concept of boundary layer, but you should remember that boundary layer is a different chapter. It's actually a book, okay? But we are talking about the result of the boundary layers, the result of it. There is boundary layer, but what is the result of it? For example, the result of boundary layer for the airplane is that you need the air engine. Okay, why do we need engine? Because there is the force, the friction force acting on the airplane. Okay, this is the sort of aerodynamic resistance. We will talk about this one in our next lectures, but you should know this one, that this is the reason that we need engines. Now, comes back to pipe flow, and due to the effect of the boundary layer, you have the pipe flow losses. Okay. And there are two types of the pipe losses. The one is, which is called as the major losses. Okay. And the second one is the minor losses. What is the major loss? If I tell the minor loss, this one, you can understand what is major loss. The minor loss is for example, elbow. Minor loss is, for example, valve. Minor loss is, for example, that connections. Okay. For example, you can see here the connection type. Use different color here. Okay. Let me first write that types of the pipe flow, then I will analyze this picture here. You can have the connections, or you can have the area change. Okay. These are the minor losses. Okay. What else do we can have for the minor losses? I've said that you can have the valves, connections, area change, etc. Okay, these are called the minor losses. At the end, you can say that these are pipe components. Due to pipe components, you will have the minor losses. And on the other side, you have the major losses. And these major losses are due to, these are the simple terms. You can say that it is due to pipe lengths. Okay. And now let's get back to this picture and understand where do we have the minor losses and where do we have the major losses. I will put the minor losses as 2 here. It means that it is minor loss, and then 1 for the major loss. So I can even ask this question for you. For the first section here, is it major loss or minor loss? You can tell me and I can write it here. Is it major loss or minor loss? There's a minor loss. Of course, it is 2, because you can see the area increases. We can show one more example here. For example, this one. These are simple questions for you, but you are Okay, this one, is it major loss or minor? Again, minor. You can see it here. This one, major loss or minor loss? Minor again. Or this one, again, minor. You know it, you have get the concept. Okay, this one is the minor loss. Or this connection here, it is minor loss. Or this connection, it is minor loss. But there are lots of minor losses. Okay, but you shouldn't get the name as that minor. It can be sometimes major. Okay, so what it means is that the name is minor loss, but sometimes it is possible that 100% of the losses is due to minor losses. Okay, but the minor doesn't mean that it will be always minor. Okay, it is just a name. Okay, nomenclature. And here you can see the valves. You can see valves. These are all valves, and these are all two minor losses, and the minor loss, and the minor loss. Now comes the major loss. Now let's see the major losses. So, for example, this part of the pipe section, okay, from that one, this part, the pipe section, you can see. So I can analyze it as a pipe section. You can see it is pipe length. There's pipe here. It is major loss. Or even, for example, if there is turning in the pipe, let me show this part for you. I will take that part here. Okay, this is the first part of it. Then you have the inclination. Then you have that part. Now you can see that there is here. So let's say this is point 1 and this one is cross section 2. In cross section 1 and the 2, you have major loss. Okay, plus you have two minor losses. One is there and one is there. Okay, that is the 1 and the 2. Even, for example, let's say that this is pipe section here, and inside that pipe section you have the valve. Again, that pipe section ends. And I take two sections here. Say that it is 1 and it is 2. Okay, 1, 2. You have the major loss, and plus you have the minor loss, because this is the valve. But the thing here is that minor. But I can ask this question for you: between 1 and the 2, which one is more important, major or minor? So between 1 and the 2, which one is more important, major or minor? What is your answer? Okay, Ali Muhammad Taghi, yes, minor is more important. Why the minor is more important? You can see that this length L is small. Okay. L is small, therefore major losses is not so important. Minor losses are important. You can see the name is minor, but it is major. You can see it is the paradox that creates. Okay, so that is the reason of the losses. Okay, now let's go back to our pipe flow again. And for that pipe flow, and you start the pipe with some pressure, so that this is manometer. You start the pipe with some manometer height here. So it is H1. Okay, but when you go next section of the pipe, so let's say this one is H total. Okay, that is, it's H1. H1 is better actually. You have the manometer height at H1, but when you go to the next section of the pipeline, you have that H2. When you go to the next section of the pipeline, you have H3. You can see the height of the manometer drops. But if I ask you this question, okay, that average velocity at section 1, this is velocity 1, average velocity at section 2, V2 average. Okay, this is our average. And the average velocity at section 3. Are the average velocities equal or not? Are the average velocities all are same? Why they are same? Why they are equal? Yes, it is due to incompressible flow, but if it was compressible, then they couldn't be the same. Okay, if it is air, for example, you can have different velocities here, because when the velocity changes for air, that velocity change is accompanied by the density change. Okay, for example, you have ρ1, so then you will have the ρ1, you will have the ρ2, and you will have the ρ3. And the ρ1 will be different than ρ2, ρ2 will be different than ρ3, because density change, that density change affects velocity change. But if it is, for example, water instead of air, for water, the densities cannot change. Densities should be the same. Okay? Therefore, the velocities are same for water. Or even you can do by mass flow rate equation. M dot is constant. M dot is rho AV. Okay? And the area is constant. The density for water is constant, and only remaining term is velocity. Therefore, velocity should be constant. Okay, this is the first part. Velocities don't change, but the pressure drops. Okay, that drop of pressure is only due to friction. This part, this is what Bernoulli says. Bernoulli says you have the loss, and then you have the loss. Okay? And the source of that loss is source, or reason is that you start with the no slip. Okay? No slip boundary condition, and then you have the growth of boundary layer due to friction. It is only due to friction. Due to friction or viscous fluid layers, between fluid layers. Okay, this is what happens in fluid flow, and therefore we need, you can see the losses here. These losses, that is the reason we need pump. So otherwise the flow will stop somewhere. You need pump to overcome that losses. That is the reason. Okay, now comes the how do we find the losses? Okay, to find the losses we will have two equations. Now let me write the equation and I will go back to this chart. Okay, to find the major losses, HL major, and this one, it is in meters. Okay, so that F and the L divided by D and the V squared by 2G. Okay, that is this one. Okay, for example, H1 minus H2. This one is HL. This one is HL, and this one is HL. Okay. HL is F into L by D, V squared by 2G. This is for the major losses. Okay, and this equation there is only major loss. And what is F and what is L, and we'll talk about this one. But if you are looking for the pressure losses, what will be F L by D, and you'll multiply with rho V squared by 2. This is the first. And now let's get to know the terms here. That the D is diameter and the L is the length. Okay, and the V is velocity, you know it. And the G is gravitational constant, which is 9.81 meters squared. And the F that comes into picture is that it is Darcy friction factor. Okay. And Darcy friction factor, okay, this one is shown as F, and this F is function of the Reynolds number that we have talked about in the beginning, and it is also a function of the relative roughness. Okay, now what is a relative roughness, and we know the Reynolds number. And the relative roughness, we can say it as R means relative roughness. It is epsilon by D. Okay, and D is the diameter, and the epsilon is the absolute roughness. So if I have a pipeline, this is the pipeline. Okay, and you can see that this is very smooth. But if I take one part of that pipeline and zoom in, when you zoom in, you will see that this pipeline is not smooth, but it is something like this one. Okay, the pipeline is not smooth, but it is rough. Okay, it is rough, and I can find the average roughness here. So it will be that epsilon. Okay, and this epsilon is shown in millimeters because it is very small value, and therefore we are showing it as millimeters. Okay. And these losses, the friction factor in major losses, F, it is the most important part. It is the function of Reynolds number and the relative roughness. And you can find the F. So one is you can use the formulas. Okay. The second is that you can use the chart, which is called the Moody chart, because Moody has invented it. And the third one is that you can use the online solvers. Okay. The online solver is the best one because the formulas are very difficult. You will see it. The Moody chart is an inaccurate method because in the chart you can have errors, but online solver is always the best. Okay, now comes that the formula. This is the formula that you are trying to find the f, and this formula is called the Colebrook equation. Okay, and this Colebrook equation is simplified to simplify, and it is called, the second equation is called Haaland's equation. Haaland equation, and then if it is even more simplified, and where you have the smooth pipes. Smooth means that epsilon is 0, the roughness is 0, and this is called the Blasius equation. Okay. You can use the Colebrook equation, you can use the Haaland equation, you can use this in the special form for the smooth pipes, you can use the Haaland equation to find the value of the f. Okay, but there is also the chart option. You can find the Reynolds number, okay, and you can find the relative roughness, which is epsilon by d, and the epsilon for concrete, for example, it is 0.25 millimeters. For that smooth concrete, new concrete, which is 0.025 millimeters, you can see it is very, very small value. Cast iron 0.15, and sewers 3, and the steel it is 0.5. You can see that the epsilon value. What you are doing is that you have to find the epsilon by d and the Reynolds number. I will give just one example, and epsilon by d is, let's say, that 0.05, and the Reynolds number is that 2 times 10 to the power of 3. Okay? And you should find the f. And to find the f, first I find the epsilon value, which is 0.05, which is this one. Okay, and I find the Reynolds number, which is 2 times 10 to the power of 3, which is this one. This is the Reynolds number. And with that Reynolds number, okay, that is the Reynolds number, and that is the 0.05. You can go with that line here and intersect. At the intersection point, we take the value of f, which is between 0.08 and 0.09. So you can see the inaccuracy of the method. This is inaccurate. What is the value? 0.085, 0.084, or 6. This is inaccurate and old method, but we use it for our lessons because otherwise it will take lots of time to find from the equations, but you can find it. Okay, but if it is laminar flow, this is part for the turbulent flow. Okay, but if it is laminar flow, you can use this line here. If it is transitional, neither laminar nor the turbulent, I have used in transitional region here, you can see it, but this region, transition region, is the most inaccurate one. Okay, most inaccurate means that it is not accurate actually, because transition region is not solved yet. But we can use for the approximations and we can get the value from here. But this dark region, you can see it is transition, neither laminar nor turbulent. Okay, but for this chart, for any of the methods here, the f value here, it is not exactly the true f value. You will have always errors. So we will have plus minus, for example, 15% errors. You have to account for that one. Okay, so this is the actual safety factor, 15% plus minus. Because these are all experimental, and the experiment never gets this exact as the reality, because the reality is more complex. The real pipeline, because in experiment, to understand the roughness, they are putting artificial roughness elements. But in reality, it is not artificial roughness elements. It is random, arbitrary roughness elements that change with length. Okay. Anyway, this is the Moody chart for the major losses. Tomorrow I will talk about the minor losses and we will solve examples. So let me stop the recording here.